Hello. All right, we're going to do lecture 12 with this series of short lectures. This is a little longer than usual because we had a short lecture last time, and I'm going to pile that material into this one. To speed things up, I'm just going to include a copy of my lecture notes. Hopefully, you can read the penmanship, and I'll just annotate on top of it. So I'm hoping that'll work out. And please let me know if it doesn't. Uh, what I want to do to begin with is finish off partial fraction expansion. And one thing that happens in partial fraction expansion is here's partial fraction expansion for z transforms. And one thing that happens is you go and you solve for the residues. Remember, the a's are the residues, and you solve for the poles, and it turns out that the a's and the p's are complex. Okay, so what you could do, but I don't want you to do, is just take the standard inverse z transform of these terms is you take a, the residue, times p to the n, u of n, and then you take this a times p2 to the n, u of n. Well, this is a terrible mess because a is complex, and you got a complex number to the n power, and it really gives us no idea what's going on here. So it's technically correct, but if you do this, if you can't read that, I'll read it to you. You lose lots of style points. Okay, so don't do that. The proper way to do this is as follows. We recognize that the poles, um, as long as the coefficients of h of z are real coefficients, which they usually are, what's going to happen is this p and that p are complex conjugates of each other. So if you know one of them, you know the other one. And the residues are complex conjugates of each other. Then the elegant way to write the inverse Z transform is as follows. X of n is 2a r to the n times a cosine omega naught n plus theta, where this a is the magnitude of the residue, a, I've written it out here, that a is the magnitude, and that theta is the angle. So if we write the residue is the residue in terms of polar coordinates, this a is that a, and this theta is that theta. Similarly, if we write the pole in terms of polar coordinates, this r is that r, the thing we're going to raise to the n power, and this omega is that omega. All right, I've shifted the page up a little bit. So what we're going to do is going to work through an example. This is actually an example in the book, but it's as good as any. And we're going to find the inverse Z transform of this x of z. Okay, find x of n and plot the pole zero diagram. So the first step is to express in positive powers of z. Positive powers of z. And that's what I've done. I multiplied this thing, top and bottom, by z squared over z squared. Okay, that's legal. And I pick z squared because that's the highest order of any of these z terms. And I'm going to multiply top and bottom through. And you see they get z squared plus z on the top, and z squared minus z plus 0.5 on the bottom. The next step is we need to factor the denominator. You don't really need to factor the numerator, although it's quite easy in this case. But you always have to factor the denominator to find the poles in order to do this partial fraction expansion. Now, a lot of times we can just use MATLAB, but I do want to write this out and to show that it's not that hard to do it by hand using the quadratic formula that you learned in high school or whatever. Okay, you take minus b plus or minus b squared minus 4ac over 2a. And then the roots, which are P1 and P2, they're the poles, are found, for our case, we've got minus b. B is minus 1, so minus minus 1, plus or minus b squared, which is 1, minus 4 times a times c. A is 1, c is 0.5. And we get 1/2 plus or minus j 1/2. Well, expressing that in polar coordinates, which I assume you can do, we get 0.707, which is our R term. That's this guy. It's the magnitude of the pole. E to the j pi over 4. That's our omega naught term. That's this guy. Okay, that's this guy. So I can express the poles in polar coordinates, and actually there should be a plus or minus here. I'll go ahead and see if I can sketch it in plus or minus, because I'm saying these are both poles. All right, so there's plus or minus there. There's a plus or minus there. So those are the poles, and we've found R and we found omega naught. Well, now we need to do partial fraction expansion. And here I've written the partial fraction expansion equation in terms of the two residues, A1, A2, that are unknown, and the P1 and P2 that are now known. Okay, and here's the method described in class. Multiply both sides by the denominator z minus P1, z minus P2. I'm just going to write them as P1 and P2 because they're sort of messy. Multiply through. On the left side, the only thing left is z times z plus 1. That's the numerator. And on the right side, the z minus P1 cancels in this term, and we get z minus P2 left over. And over here, what we're going to get is z minus P1, because the z minus P2 cancels when we multiply that across. And the z terms there I show getting canceled, that they all divide out. And we can find, now we can find A1, which is this guy, by letting z equal P2. Excuse me, we can find A1 by getting rid of this whole term, which happens when z equals P1. So that's what's happening here. I've got z plus 1 is equal to A1 times z minus P2, and this term has gone away, and we've let z equal P1. So solving for A1, we've got z plus 1 here. We're going to divide through by z minus P2, and this term has gone away again, and I'm going to let z equal P1. Plugging in what P1 is, it's just a little complex arithmetic. P1 is 0.5 plus or minus j 1/2, but we're taking the positive root, and we add that to 1, and we get 1.5 plus j 0.5. And then this whole denominator, we've got P1 minus P2, and you see the only thing left is the j term. And dividing j into that, you get 0.5 minus j 1.5. In polar coordinates, it's 1.58 angle minus 71.6. And you notice we don't even need to find the second residual. We don't need to find A2, right? Because when we're going to plug everything into this thing, I only need to use A1 to calculate A and theta. All right, so to finish this example, remember we're going to plug in A, R, omega naught, and theta. We got A and theta came from the residual. Remember, the residual was 1.58 with an angle of minus 71.6 degrees. And we get R and omega naught. That's the polar coordinates for the pole. And we got 0.707 is the magnitude, and pi over 4 was its angle. And we plug all that into x of n, to this formula for x of n, and we have a very nice result. It's completely real, which it should be, and it's a decaying exponential. We can kind of see it's decaying exponential here. I've sort of graphed it out. 0.707 to the n is multiplying this whole thing, so it provides kind of an envelope that the rest of this thing gets multiplied by. So there's 0.707n. Here's the cosine. Okay, there's the cosine. It's shifted, so I just kind of, just to get a generic sketch of what this looks like, I drew a cosine. But it has to fit within this envelope, since a cosine has a unit magnitude, and you multiply by 0.707 to the n, it's going to fit within this envelope. Now the whole thing is going to get multiplied by a constant, which I'm not showing here. I just want to get a kind of an idea what the shape of this is. And within this decaying sinusoid are our samples, and they're discrete time, and we show them with a stem plot. And you see it kind of decays forever. And for negative time, we get, of course, zeros. You can also plot the pole zero diagram. That was what was requested. The numerator had z times z plus 1. That was the numerator. So that provides us with the zeros. There's one zero at z equals 0. That's that one. And there's another 0 at z equals minus 1. You see I've plotted those two on the pole zero diagram. You always start by drawing the unit circle, just to give us a picture of where we're at, and that'll have more meaning as we go along. The two poles were at 0.707 plus or minus e to the plus or minus j pi over 4. So there's the two poles as a magnitude of 0.707. Okay, it doesn't quite go out to the unit circle, which has a radius of 1, and it has an angle of pi over 4. So that's that angle, 45 degrees, 45 degrees. And this is plus or minus, so we have another one over here. And that completes that homework example.